Did any exciting or burning questions come up during the coffee break? Okay, it better be exciting or burning. Just kidding, yeah.
Is it possible to consistently add the axiom of choice?
I think on its own the answer is yes. Yeah. And in fact, I'm pretty sure it's defined in one of the standard libraries somewhere. Hello? 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 Yeah. Any other questions? Okay, let's get right back to it. Okay, where were we? So we had just seen how to define inductively, we saw how to define inductive properties of a particular piece of data as an inductive data type, right? And the even example we saw was just defining a property on one particular data type, in this case nats, right? But you can, there's nothing restricting us to just one. Defining a property of a single data type, we can define it over multiple ones. And in particular, we can define a two-argument proposition or a relation as an inductive data type as well, right? So here's an example of how we might define less than or equal to as an inductive data type in coq. So here LE is less than or equal to, as you might expect. And what's the right way to read this? Well, we're going to build a new kind of proposition that on two different natural numbers. And in particular, we're going to say there are two ways of building up evidence of this proposition, and correspondingly two constructors, right? So we're going to say every natural number is less than or equal to itself, which is true. And also, it is the case that if one natural number is less than or equal to some other, it's also the case that it's less than or equal to a successor, or adding one to that number, right? And then we have a nice notation here. And you can imagine using these rules to build up a proof that any particular number is less than another one by first applying less than or equal to n, and then just applying successor as many times as you need to get to the the number in the right-hand side of the inequality. Yeah. All right. So here are some sanity checks. I guess we'll work through these in class. Let's see, just to see get a little bit more experience of using these inductively defined propositions or relation in action. Let's see. I wish there was some way of hiding these proofs. Is this readable to the people in the back, or should I blow it up slightly more? I see thumbs up. Okay. Right. So if we want to show that 3 is less than 3, well, we have the constructor for we just need to apply that constructor, len, and we're done. If we want to show 3 is less than 6, we can do what I said before. We'll just reduce this to showing that 3 is less than 5. And then 3 is less than 4, and then 3 is less than 3, and then we can apply the constructor len. I guess we could have also applied this proof that we just wrote up above for convenience, and we're done. Interestingly, again, if we have some evidence, inconsistent evidence as an assumption, we can do inversion on it to derive a contradiction. So here we're saying, if you give me some evidence that 2 is less than 1, I can give you a proof that 2 plus 2 is equal to 5, right? And when we do inversion on H1, there are two cases to consider. In one case, it would have to be the case that 2 are equal to 1. So LE1 is just not even considered. That's obviously not true. And inversion discharges that case automatically. And then alternatively, there's the case that 2 was less than or equal to 0, and from which the LENS thing, so we add 1 to 0, and we get the original conclusion, right? So once we've done that, let's see, where's H2 here? So we have this proof that 2 is less than or equal to 0. If we do inversion on that, we're done. Because there is no number such that adding 1 to it will get us to 0, and 2 is not equal to 0. So the two cases are just discharged automatically by inversion. So sort of the key bit here is that if we have some piece of evidence, if we have some assumption about an inductively defined proposition or relation that's inconsistent, that's obviously contradictory, it is possible to derive those contradictions, derive false from it, using the inversion tactic. Yep. Any questions about that? Yeah.
Inversion is about the injectivity of constructors and their disjointness. But here, we don't have any equality of constructors proposing injectivity or disjointness claims. So what is inversion doing?
The question is, what is inversion doing here? With the assertion that inversion is about proving injectivity and disjointness of constructors. And the answer to that question is inversion is actually a hammer that is doing many things in addition to just reasoning with those facts. And and we're going to see precisely exactly, we're going to get into a little bit more detail about how inversion works later in this lecture. So we'll revisit that question when we get to that point, okay? But the sort of key takeaway is that inversion is doing more than just proving these constructors are disjoint. In particular, you can imagine it's showing there is no way that you could have applied a rule to derive this particular proposition that you have as an assumption, because it's inconsistent with the ways we have of building up that evidence.
Since inversion is such a big hammer, is there a simpler way or a simpler tactic to use to discharge this proof?
The question was, could we use a simpler tactic to discharge this proof? The answer is yes, but it would be more tedious too. So in some sense, if you have a contradiction, it's best to bring out the largest hammer you have, which is, I guess, a little bit wishy-washy of an answer. But yeah, we could discharge this in other ways. It would get, yeah, I'll leave it there. Okay. Any other questions? Okay. Okay, we worked those sanity checks. So now that we've defined this we have this inductively defined relation, less than or equal to, we can also define strictly less than, right, as in terms of this inductive data type. So as an example, we can say that a number n is less than m if it's the case that adding 1 to that number is less than or equal to m. So we don't actually need to define an additional inductively defined proposition or relation in order to define less than or equal to, or strictly less than. Here are a couple more examples of relations on numbers, right? Here's square of next nat, next even. I think what's sort of an interesting and cool thing to note here is that if we defined square of, if we define this as like a Boolean function, how would we do this? Well, what we'd probably have to do is figure out some way of, well, I don't know. One way to do it would be define like a factorization function and see if you can factor this into a square of two numbers, and then see if these two factors are the same and they're equal to the one that you passed in. So you have to do this computationally. This inductively defined proposition, you don't have to worry about any of that, right? It's very declarative. There's no sort of information about how to algorithmically compute this square, right? It's all sort of embedded into this declaration. So in this way, inductively defined propositions can often be much nicer to write and use to specify properties than their Boolean counterparts. Yeah. Are there any questions about that? Yeah.
So the first two types you've written can be rendered in terms of the equality proposition, but instead you've decided to make them as inductives. Would we want to use equality with functions in place of these kind of inductives? Or what kind of power do these give us instead of using equality and functions?
Right. So I think certainly in the first two cases, there's nothing really. These don't really add anything on top of equality, in much the same way that this LT, the strictly less than, doesn't really add anything on less than or equal to. It's just sort of a nice convenience. So practically speaking, I don't think working with defining square of or next nat as equality, as definitions in a similar way to LT, would be any nicer than working with these inductive data type definitions. I don't think you'd buy anything. Where it does come into use, really nice use, is if you have multiple cases, like here, this is much nicer to work with than having big disjoint, like sequences of ORs, right? So if you think about defining fix, that function, the in function that we defined before that like iterated over a list and built up a bunch of disjunctions, it's a little bit more natural to have two different rules for that, right? You'd have a rule for it's the head, and you'd have a rule for when it's a member of the tail. And so in that case, when you have multiple, basically multiple cases, inductive is much nicer to work with. In addition, doesn't have to be total. And in addition, if we defined in inductively, we don't have to worry about putting this sort of spurious false case, right? We just, oh wait, forget I said that. We're going to see that in a second. Okay. Are there any other questions? Okay, right. So to see a more in-depth example of inductively defined propositions that aren't even or less than, we have this little case study in Software Foundations of how we could embed a really simple language, which using and define properties on it using these inductively defined data types. And you can imagine as the week progresses, you're going to use the concepts for this simple language to generalize to actual programming languages and properties of those programming languages and programs written in those programming languages. So this is sort of like the simplest example of a little, we'll call it a programming language that you might want to reason about. And it has a lot of the features that these larger examples will also have. Okay, so here's our regular expression data type. What are our constructors? I don't think there's anything exciting here. There's an empty set, there's the empty string, there's characters, there's sequencing or app is what it's called. There's union and there's star. I think this is a pretty reasonable subset of the regular expression language if it's not total. Of course, by itself, there's nothing, so this is just an inductive data type. We could build up trees using these constructors, but there's no meaning associated with them, right? So how are we going to assign some meaning to terms, some semantics to terms built up using these constructors? And here's what we're going to do. We're actually going to come up with a set of rules that relate a regular expression to a particular string. And these will give some sort of semantics for how we can interpret a particular regular expression. Okay? So how are we going to think about this? Let's think about what the matching rules for regular expressions are. Okay. I guess they're all written on the slide. I probably should have waited and had you. So like for instance, empty set doesn't match anything, right? The empty string matches the empty string. Okay, that makes sense. The char matches the one character string with exactly the character in it. App matches the append of two strings and so on and so forth. Perhaps most interestingly, right, when does union match something? Well, there are two cases there, right? Either the string matches the first regular expression or it matches the second regular expression, right? And then, well, otherwise straightforward. As a special case, the sequence of strings may be empty. So star re always matches the empty string no matter what the regular expression is, right? Okay, so here are the rules for matching regular expressions in English. I hope people think they seem sensible. How can we embed those as an inductive data type? Well, basically we're going to have one rule for each of those English clauses, the English sentences we had up there. So here we go. We're going to define a new proposition. It's going to be a relation on lists of, we'll say characters, in this case T. It's an arbitrary type. And then there's going to be a regular expression, and then there'll be a proposition. And this is going to embody all of the possible ways that a particular string of characters could be matched by a regular expression. So there's the rule for empty, namely if it's the empty string, we're good. If it's a concrete character, then it's only going to match the char constructor. Mapp looks straightforward. Interestingly, for the union constructor, we're going to have two different rules, right? One saying we match the first regular expression, one saying we match the second regular expression, right? And then For star, we're going to have a special rule distinguishing when we match the empty string. We always match the empty string. And for app, it's what you'd expect. So hopefully these look relatively straightforward. There's basically a one-to-one correspondence with the rules on the English rules. There's also a one-to-one correspondence with these in the definition of this matching construct as an inductive relation. So here are the rules for it. We're going to have the special tilde equal tilde syntax for matching, but this should look fairly recognizable to anyone who's familiar with inference rules, right? And again, there's one rule per constructor of this inductively defined relation. Any questions about this? You could imagine doing something simpler for a programming language, right, where you have, instead of a regular expression, you have a program, and then you assign some meaning to it as an additional part of the relation. Okay, so here's a good question, and this answer is a question we had earlier, I think asking about if we needed a rule for even one. So in this, we had this clause in our English definition, right, that said the expression empty set does not match any string. We don't actually have that corresponding rule in our set of definition, in the definition of our inductive relation. Do we need to add something to account for this English definition? So think about it. Don't answer yet. I will, and then I'll ask you to raise your hand. Or raise your hands when you have the answer. Okay. What's the answer? 1, 2, or 3? 3. Right. No, the lack of a rule actually gives us the behavior we want. Okay. And why is this? Someone want to volunteer to? Yeah, go ahead.
Because of the, sorry.
Okay.
Don't remember.
Because it's not derivable.
Right. So if we ever, that's exactly right. If we ever had as an assumption that the empty set matched some string, we could use inversion on it, and it would, that would be a contradiction. There is no way of building up evidence of this fact. It's just not allowed. And so in some sense, in much the same way that these rules allow us precisely specify exactly which values are included in the relation, which means they also precisely specify which values are not included in the relation by exclusion, right? So excluding something from this relation is just a matter of making sure there are no rules that can be applied to derive it. Right? We don't need to explicitly call it out. Yes?
Would it be useful to add a lemma saying that no string would match the empty set?
Yep. So I think the question was, would it be useful to add a lemma, witnessing the fact that that empty string doesn't match any string? And indeed, I think that would be very useful, right? You can derive this fact from the definition of the inductive data type, and that's a very useful sort of sanity check that will probably be of use when you're working with assumptions of this form. Yeah, that's a great suggestion. And indeed, these sorts of sublemmas, sort of verifying that your specification actually meets your informal mental specification or your English specification, can be quite useful. Yep. Do I want to say anything else about that? I think I don't want to say anything else about that. Because it might get confusing. Okay, so let's just see a couple of examples of this relation in action, right? So we can actually essentially test the sanity of our relation by seeing if the values we want to be included into it actually are included, right? And how do we do that? Well, we can just build up proofs that show particular strings and regular expressions are included in the relation. So as an example, we can show that the list with 1 in it matches the regular expression char1. We just apply the constructor. That's pretty straightforward. Similarly for app, we can do the same thing by just applying these constructors. And then finally, here's an example. We want to show that something is not included in the relation. So how do we do that? We're going to want to derive false. So we say it is not the case, using logical not, that that the list containing 1 and 2 matches the regular expression char1. And how do we prove that? So we say, again, just to drive the point home, this is equivalent to saying this statement implies false. We're going to intros the assumption, this assumption about whether or not the string matches the regular expression, and then we'll do inversion on it, and it'll just completely discharge the goal. Okay.